Hey class, this is Mr. Roberts. Time to take a look at some homework. Today we are in section 2.2.1 and starting with question 47. Mrs. Ong's class conducted an experiment by rolling a marble down different lengths of slanted boards and timing how long it took. Different lengths of slanted boards. Different lengths of slanted boards. So if you have it's not telling me the angle of inclination. Maybe the angle is always the same. But if you have a board that's like long, it looks like it takes longer to roll down it, right? If you have a really short board, it takes less time. And if you have a board that's 0 inches long, it takes no time at all, right? So this data is very well organized, right? I seem to think that there is an association here. Um, what does it say? This is the results are shown at right. Describe the association. Refer to the math notes in this lesson if you need help remembering how to describe an association. Well, we might take a look at the math notes. That might be a good idea to do, but I think I understand the association here. I would say just looking at it, we could say that the longer the board is, the more time it took to roll down it, right? The greater greater the length, length, of the board, board, the more time it takes to roll down the ramp, I guess, of the ramp made of the board, RAMP. So I would say, not ramp, RAMP. So I would say that as the length of the board increased, the amount of time also increased. So I think maybe we can say it's maybe a positive association. Let's take a look at the math notes real quick and then see if we can help clean this up. So this is titled Describing Association. An association relationship between two numerical values can be described by its form, by a form, a direction, a strength, and an outlier. Form, direction, strength, outliers. The shape of the pattern is called the form. So if I look at our problem that we were looking at, to me it looks like the form might be maybe some kind of an exponential curve, right? And it's in here, and like this might be the form of it. So I don't think it's linear. I think it's kind of a curve. Um, the form. So I should write that down. Form. Well, this might change my answer completely. So the form is a curve. It's not a linear. Doesn't look linear. What else do they say? The form of the association, linear or nonlinear. Oh, okay, so nonlinear. I said curve. That's okay. The form can be made of clusters of data. Okay, if one variable increases as the other variable increases, the direction is said to be positive. Well, that's what we have, right? We've got a positive association. Okay, so it's a well. Let's see. Form. They use the word nonlinear. Nonlinear, and its direction is, what did they say? Positive. It says if one variable increases as the other variable increases, the direction is said to be positive. Okay, so we've got the form, we've got direction, and our direction is positive. And that's pretty much all I caught with what I said, is that as one variable increases, as board length increased, the time increased. So I got that it was a positive, but I didn't get the form. And then they're missing two other things. There is said to be a negative. Oh, if one variable increases as the other variable decreases, there's said to be a negative association. We don't have that. If there's no apparent pattern in the scatter plots, then the variables have no association. Well, I think we've got an association. And then strength. Strength is a description of how much scatter there is in the data away from the line of best fit. Some examples below. So when I look at the graph that we had, I would say that we have a very strong positive association. So it was very strong. So I'm going to come back up here and I'm going to say the strength is strong. The strength is strong. Strength, STRENG. The strength of the association, it was a strong association, right? And it would look weaker if these points were like, instead of being like all clustered up on this curve, this line of best fit, maybe they would be like some below, some above, and they kind of scatter out from it. But they're just hugging this curve. So I would say that this is a strong relationship. And then the other term that I want to come up with is, U, there we go, is the outlier. It says an outlier is a piece of data that does not seem to fit the data. And when you see there's this one variable right here, most of it seems to be in the same band, but this one doesn't fit. And so there's an obvious outlier there. And back to here, I don't see any outliers. So outlier, Outlier, I would say none, right? So its form, it's non-linear, it's not a line. Even though like this part looks pretty linear, right? For the most part, because of this thing in here, I'm tending to think it's not linear. But if you wrote down linear, maybe you wrote down linear and you said that these were outliers, right? If that's what you think, that's okay. But I'm saying it's not linear. Direction is definitely positive, right? In general, I can see it's increasing. It's strong because most of the points live right along this line of fit. They're not going all over the place. And I would say that there's no outliers. So that's what we're looking for there. Let's go on to question 48. 48. Miko has been going to barbecues this summer and keeping track of the number of people in attendance and the total number of burgers that were eaten. Uh-oh. Burgers versus people. His data is shown in the table below. Graph this table. Should the points on the graph be connected? Okay, let's graph it first. Whoops. Oh, no. Let's see. Not you. So I have set up my x-axis to accommodate people, and I needed to get up to 19 people, and you can see I'm counting by 2. So each one of these changes in x represents 2 additional people, and I ended up at 20 people there. And then for my y-axis, each one of these was 2 burgers. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 burgers, and I made it all the way up to 30 burgers. So I'm going to go and plot these points. The first one is 2 people and 3 burgers. That's pretty easy, right? Here's 2 people, and that would be 2 people, 2 burgers, but I have 2 people and 3 burgers. So there's my very first data point. Let me plot the rest of those. Okay, so with all those data points listed there, I have a very nice, strong association. It appears, this is a surprise, that the more people you have, the more hamburgers you may eat, right? So it's people versus burgers. Um, it's a positive association. It looks relatively strong. There's not a lot of data here. So I've got the direction, the strength. It appears to be linear. Um, and I would say it's a proportion. You got 0 people, 0 burgers. That makes sense. And what was the other word? Outliers. I don't see any real obvious outliers here. So I don't know that they asked me to do that. They just said graph this data. Should the points on the graph be connected? Oh, should they be connected? No. Although you could eat, like if I'm going here on burgers, this is 2 burgers and that's 1 burger. This is a half a burger. You could eat half a hamburger, right? But going the other way, I don't like talking about this would be 2 people, this would be 3 people. I don't like talking about a half a person, right? So I would say I would leave these disconnected. I would say this should be discrete because I don't like talking about parts of people. And you can see I just wrote a response. Data, I don't think this data should be connected because we don't talk about just a half a person, right? We talk about full people. And this comes down to the idea of whether or not the situation is continuous. Oh, continue O-O-U-S, continuous, I think, or discrete, D-I-S-C-R-E-T-E. So in a continuous situation, right, we could connect the dots, and that would be like we could talk about, water, volumes of water and things like that. Discrete, people, buses. Um, we don't talk about taking 1.2 buses. Anyways, let's move on. Question number 49. It says, what is the slope of the line? What is the y-intercept of the line? Graph the line. Oh, that's great. This slope right here, by the way, it does not say sketch the graph. It says graph it. The slope is up 1 over 2. So y increases 1 unit every single time x increases 2. And the y-intercept is at 4. By the way, the location of that is x would be 0 and y would be 4. So we got that. Now it's time for the graph. And even though it does say graph, it doesn't say sketch. I can't find my digital graph paper I always use. So I'm just going to use this. So I've got my x-axis. I've got the y-axis. My y-intercept occurred at positive 1, 2, 3, 4. No, my y-intercept. Oh my goodness, Mr. Roberts, your y-intercept is at negative 4. Hello, that means something. That's right. So it's at 0, 4, or 0 comma negative 4. Oh my gosh, I'm glad I caught that. 1, 2, 3. Here's negative 4. So I'm going to start here, and then my slope pattern is I go up once for y, and then x increases by 2. Yeah. Once up for y, x increases by 2. Yeah. Let me grab my ruler here. There's the ruler. Wait, where'd you go to? Ruler. There's the ruler. And I'll just line this up here. So I got roughly that slope pattern of 1/2. And there we go. And I'll go ahead and label this. This is y equals up 1 over 2 times x and then minus 4. All right, let's move on to question 50. 50, it says if f of x is equal to 3x minus 9 and g of x equals the opposite of x squared, calculate the value of, okay, f of negative 2. Oh, I like this. F of negative 2. So you can see the definition of f, right? So I want f of negative 2, and that's going to equal 3. Now, I use these parentheses, and that's where I put my x. 3 times the negative 2 and then minus 9. So that looks like 3 times negative 2 is negative 6 minus 9. We're looking at negative 15. So f of negative 2 is negative 15. Let's try g of negative 2. Okay, so g of negative 2. G of negative 2. It's the opposite of x getting squared. And x getting squared is negative 2. So if you look at it, I'm going to square the negative 2. I'm going to multiply negative 2 times negative 2. And when I do that, I get negative 2 times negative 2 is positive 4. So this is the opposite of positive 4 or negative 4. So when I take the opposite of x squared, right, this ends up becoming negative 4. Next question says, find x if f of x is 0. Oh, okay. Remember, f of x is 3x minus 9. And they're saying, hey, if the output, right, remember what f of x represents? It's the output. So it says if the output is 0, right, if the output is 0, find x. So here's my output. F of x represents the output. So if the output is 0, for this function, what is 3x minus 9. What is x? Okay, I can deal with this, right? I can figure out what x is. So the output is 0 and the function is 3x minus 9. I'm going to add 9 to both sides. So I get 9 is 3x. I'm going to divide both sides by 3. And when I do that, I get 3 is x, right? X has to be 3. So I think 3 should give me an output of 0. And if I come up to the original function and I say, hey, if I put 3 in there, that's 3 times 3, and 3 times 3 is 9. 9 minus 9 is 9. So yeah, if the output is 0, the input had to be 3. This one you could almost kind of look at and see, but I want you to pay attention to that technique, right? Because if you're given what the output is, right, it says find x if the output is 0. Notice I just said, okay, the output is 0. I put it here. I put it because f of x represents the output. I put 0 there and then solved for x. And then finally it says, what is g of m? Oh, g of m. What is g of m? And remember, m was the opposite of m squared. So that's what it is. That's the answer, right? If I take m and I put it into g of m, right, what I'm going to do is I'm just going to put m there in the place of x. So it becomes the opposite of m squared. That's it. So that's the answer for part D. Well, that's clever. Let's move on to 51. It says, what is not part of the domain, right? Those valid x values that you can put in of this function. What cannot go into that function? Well, you know what it is. My big problem here when I see this is I cannot divide by 0. So I know that x plus 5 cannot be 0. It can't be 0. So what do? I'm going to set it equal to 0. Well, that's weird. You know it can't be that. I know. But if I set it equal to 0, it's going to tell me what x can't be. If I solve this for x, right, I get that x can't be negative 5, right? The moment x is negative 5, I get a problem with this here domain. So we're just going to write down, hey, right, if x is negative 5, this is a bad day because I'm dividing by 0. So I could just say x, or I could just say, well, I'm going to just say, I'll say negative 5 is not in the domain of this here function f of x, that particular function f of x. It's not in the domain. And that's it. We're done. All right, great. Have a good evening. I'll see you guys in class tomorrow.